Hello everybody, I'm going to show you guys some of the weirdest numbers that I've ever found. This is my new favorite number. Why is that? It's because if you multiply by any number from 1 through 6, you're not going to get any new digits, just different cycles of this number. But what I think is interesting is that if you multiply it by 7, you get 999,999, and that relates to how 1/7 is equal to 0.142857 repeating. Same thing for 2/7, 3/7, 4/7, 5/7, 6/7. Yeah, like that. It'll give you different cycles too. There's other cyclic numbers out there, and they have to do with prime numbers. I'm not going to explain it now, but pretty cool. 998,001 is a pretty interesting number, because 1 divided by this number will give you all the 3-digit numbers from 0 to 999 in order. But 998 is not included. That kind of makes me sad. When I shared 998,001 with you guys, you may have noticed that 998 was missing. If you guys are sad about that, we'll take a look at this number right here. 13,717,421. Looks like a boring number, but this number divided by 1,111,111,111 will give you 0.01234567890, 0.123456789, which is absolutely ridiculous. I can't believe that. But the crazy thing is that this number times 9 is 123,456,789. Let's take a look at 3,435. This is my 5th favorite number, but watch this. So 3 to the 3rd power, plus 4 to the 4th power, plus 3 to the 3rd power, plus 5 to the 5th, is, of course, 3435, which is insanely ridiculous. I really like this, and it just lines up so nicely. It's like 34, 35. They're in order. And the weirdest part is that this is the only number that actually works like this. 2025 is a pretty weird number that we see everywhere. And why is that? It's because, first of all, it's 20 plus 25 squared, like all of them. It's also the sum of all the multiplication tables from 1 to 9. And also, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus 9 all squared. And also, the weirdest part about that is that it's 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed plus 5 cubed plus 6 cubed plus 7 cubed plus 8 cubed plus 9 cubed, which is ridiculous. Speaking of 2025, now that we are in 2025, I wanted to say we are closer to 2050 than we are to 2000. Okay, that's enough nostalgia. Right now we're going to look at 357 sextillion, 686 quintillion, 312 quadrillion, 646 trillion, 216 billion, 567 million, 629,137. It just looks like a huge number, but if you take a look at it, it's a prime number. But if you remove the last digit from the left side, you get 57 sextillion, 686 quintillion, 312 quadrillion, 646 trillion, 216 billion, 567 million, 629,137. That's also prime. If you keep doing that, you'll eventually get all prime numbers. I'm having trouble saying it because it's a big mouthful. But this is the largest left truncatable prime. It also works with 73,939,133, in which case you do it from the right side, and all the numbers will be prime. 6,174 is a pretty mean number. That's because this number appears as a constant, and doesn't want you to go any further. I'll show it to you. Take any 4-digit number without repeating digits. Like you can't pick 1,111, but you can pick 1,110. Rearrange the digits from greatest to least, and then rearrange digits from least to greatest, and then subtract the 2. Keep doing this. Do it again, and again, and again, and you're going to see this number keep showing up, which is pretty mean for this number. It also works with 495, which is another kind of constant. It does it the same way, except for 3-digit numbers. 137 is a pretty interesting number, because for one thing, it's prime, and if you remove any of the digits, and any of the digits, you can remove 1 or 2 digits, you're not going to get any composite numbers. Even though 1 isn't a prime number, it's still not composite, so that still kind of counts. But Like, for example, remove the 3, you get 17, that's prime. Remove the 7, you get 13, that's prime. Remove the 1, you get 37, that's also prime. And remove the 1 and 7, you get 3, that's prime. And remove the 13, you get 7, you get prime. Which is pretty cool. So, I call this no composites inside. Take a look at this. It's 2 to the 5th power times 9 squared. What do you suppose this equals? It's 2,592. Just take the exponents, drop them down, and then you got your answer. Pretty cool. This number might look pretty random, but 6,174 brought me to this number. That's because I did the same thing that you do to get 6,174 as a constant for 6-digit numbers, and I end up getting this number, 851,742. But if you look at it closely, you can actually see it's actually the exact same digits as 142,857, which we talked about earlier. So we see that number a lot. But if you take some numbers, like this is the number that I eventually ended up with when I was working with some of them. So, like, take this number, rearrange the digits from greatest to least, then rearrange the digits from least to greatest, then subtract the 2. Keep doing this, and then you're eventually going to get this number again, and then the cycle's going to repeat. And it's going to repeat again, and again, and it's going to go on forever. Kind of like 6,174. Except it's in a cycle, rather than, like, being a constant and stuff. Here's another extremely big number that I heard about. 684 quadrillion, 912 trillion, 110 billion, 217 million, 988,900. And you can start dissecting it by making it part of a right triangle. Like if the hypotenuse is this big number, and this is a squared, and this is b squared, then that means that this would be c squared. So if you do the square root of a, b, and c, you're going to get these. But these numbers might seem pretty random, but if you divide a by b, you'll get 3.14y59265, which is ridiculous because it's an extremely close approximation for pi. This is 8,128. It is a perfect number. What does that mean? It means that the sum of all of its factors, except itself, equals itself. So, to get this number, you just gotta add up all of its factors, and then you got it. Pretty cool, right? This is my second favorite number, 588,235,294,117,647. And it's a cyclic number, like 142,857, except you have to multiply it by any number from 1 through 17. But this number is the next one that comes after that, and 142,857 is the only one that doesn't begin at 0. But this one, just basically multiply by a number from 1 to 16, you won't get any new digits. But you just get different cycles of it. But multiply by 17, you get 9 quadrillion, 999 trillion, 999 trillion, 999 billion, 999 million, 999,999, which relates to how 1/17 and 2/17 and 3/17 and so on in fraction form are this string of 058823529411767, repeating.